Picking up where we left off last time. So I'm on page 2 of the section 1.5 sheet that I gave you last time, or you've printed out if you're watching the video online. Okay, so at the top is another inequality. It involves fractions, so it incorporates 2 of the things we talked about last time. So start there. Go ahead, and I'm going to give you a minute or 2 to make as much progress on exercise 6 as you can. When we talked last time, what's our process for when there's a fraction? What ought you be doing right now with this? I'm sorry, I didn't hear you. We're going to find a common denominator, because what do I want to do? I want to get rid of the fractions. I want to clear the fractions. So what is the common denominator of these 2? Perfect. Okay, so hopefully you multiplied everything by 14. As I mentioned last time, but I love to repeat myself, so hopefully you'll remember something, is don't forget to multiply the right side of this by 14, even though there's no fraction over there. Okay, you can't put the equation, or excuse me, you can't put the inequality out of balance by just multiplying one side by the stuff. So here, 2 goes into 14 and leaves 7. So 7 times 3 is 21x. 7 goes into 14 twice, so 4x times 2 is 8x, and then that's greater than or equal to, because we multiplied by a positive 14, not a negative, so we don't flip that sign. And then negative 5 times 14 is negative, it looks like that's going to be 7. At this point, this should be pretty routine. I'm guessing 21 and 8 is 29. Divide both sides by 29. I don't have to flip the sign because this is a positive 29. So it's greater than or equal to negative 70 over 29. 29 is a prime number, so this is not going to reduce at all. I am golden as far as the fraction is concerned. Don't make a decimal out of it. Keep the answer exact. And then the last thing to do when you have an inequality is I have to write this in interval notation. So if all of my values are going to be bigger than negative 70 over 29, is this the lowest or is this the highest? It's the lowest. Okay, so negative 70 over 29 is the lowest. Infinity is going to be the highest. We always use a parenthesis at this end, and because of the equals, we should have a bracket at this end. Any question about that before we're just about to wrap up our talk about solving inequalities? I got two more quick examples because there's just a couple things I have to remind you about. All right, then please do example 5. It's an equation. Go ahead and solve that. Just in case you've forgotten, this is one of the special cases, so I don't want to leave you hanging too long on this. So on the left, 5 minus 4x, there's nothing much to do there. On the right, again, we've done all this, so hopefully it's not too mysterious. I'm going to distribute. Got some like terms over there. 5 minus 9x is going to be negative 4x. At this point, you might see that something goofy is going on, but I'm just going to take this one more step. I'm going to go and get all of my x's on the left, as I've told you repeatedly as my habit. So when I add 4x, what happens to the x's on both sides on this problem? Cancel on both sides. So let's see what happens when the x's cancel on both sides. I've got a 5 over there. I've got a negative 9 over here. I've got no x's anywhere. So what this is called, I get down to the bottom, this is called a contradiction. Okay, this statement right here is never going to be true. 5 is never equal to negative 9. There's no x here to make it balance out. So this is a contradiction. What this is telling you is that at the beginning, there were no x values up here. You can try for 100 years if you want. There is no x value you could plug in that's going to make both sides equal. And so when you come across a contradiction, when your last statement that has no variables in it, when your last statement is not true, then that means there's no solution. And the way in this class that we write no solution, since we're giving all of our answers as sets, is we write that as an empty set. So there's my squigglies with nothing between it. There's my empty set. So just not to waste your time, well, I'll waste a little bit of it. Exercise 7, take a couple moments, simplify that, and then we'll talk about what that special situation means. Okay, so again, this is going to be another special situation. You got a little simplifying here, dude, just to make the problem a little spicier. So when I distribute the 3, I've got 3x plus 6. When I distribute the negative 5, there's negative 5x minus 10. The right side, there's nothing to do over there. When I combine my like terms, I've got 3x minus 5x, that's negative 2x. 6 minus 10 is negative 4. At this point, you could probably answer the question, but I'm going to just take one more step. Once again, I'm going to get all my x's on the left. So I'm going to add the 2x to both sides. But this time, instead of ending up with a contradiction, I end up with the same thing on both sides. -4 here, -4 there. Again, no x's, there's no variable. Okay, this is not what the conclusion you come to if there's any sort of variable left. When you got the same thing on both sides, it's called an identity. You got the identical thing. What this is communicating to you is you don't have to try very hard. Any value you pick up here is going to create a true statement. Okay, because the equation is always in balance. Okay, so when you come up with an identity, what that means is all real numbers are your answer. Okay. And we mentioned this when we talked about interval notation. The way that we write all real numbers is -infinity to positive infinity. So the solution to an identity is all real numbers. Okay, the last few problems that we have to talk about involve graphs. And I've mentioned to you before the significance of graphs here. We're going to spend, after the test next week, when we come back, we're going to spend pretty much the rest of our semester creating graphs, interpreting graphs, having just so much fun with graphs. So this is kind of your first dose of that. So want to make sure that we feel good about this. So I'm going to turn over to this camera and make sure that I've got it. There we go. Let's zoom in a little bit. Okay, that's lovely. And we're going to lock it so that it doesn't do all sorts of weird things like that. Okay, so you've got these two graphs. Now, first thing I got to tell you is I couldn't figure out in Microsoft Word how to label the lines on the graph well, so we're just going to label it ourselves. So on this one, please label the blue line f of x, and the red line we're going to label g of x. Okay, the blue one is f of x. The red one is g of x. So we're asked to do two things on this example. The first thing down here at the bottom is I want to know where is f of x equal to g of x. Now, before we do this problem, I just want you to remind me of something we said already notationally. What does f of x? F of x means what value is that? It's the y value. That is our function notation for the y value. So what that's telling me is whatever x value I plug in, I'm coming up with this y value, this f of x. So what we're saying here is I want to know where the y value for f is equal to the y value for g. Now, physically, what's happening on the graph where their y values are equal? They intersect, they cross. Okay, so here's how you're going to notate your answer for this equation. Here's where they cross. I'm just going to make a nice cute dot right there. That's the y value that I just put that dot at. What is the input? What is the x value that produces that y value? Yeah, I'm just going to make a little dotted line here so that we're all clear. The x value that creates that y value is 2. That's the solution. That's where we have equality. So my solution set is the set with 2 in it. Before we do the inequality, we're going to slide the sheet here to the left. And again, we're gonna label the blue graph f of x and the red graph g of x, for better or for worse. And I would like you to answer the same question for that graph. Just do the equals. What is the solution set for where f of x is equal to g of x? Once again, that happens at the intersection, which is right here. So what x value did you come up with where those two things are equal? -3. Did anybody get something different that we have to talk about? I cannot stress to you how super important this is. Okay, I'm going to put a couple problems like this on the test because it's probably one of the most important things that we've talked about in addition to the definition of a function and doing that.
Okay, being able to read a graph. Now this next part, this is sometimes where students stumble. So if you're not seeing this, you need to interact with me and talk to me. So the next one is I want to know, where is f of x bigger than g of x? So again, remember the function notation is representing my graph, or excuse me, representing my y values. So I want to know where the y values for f are bigger than the y values for g. Well, we just found out where they're equal. They're equal at this intersection. So the answer must be either on the, on the left side of that or on the right side of that. So which side would you propose to me the function values for f are bigger than the function values g, left or right? Okay, so I heard a little bit of both. Okay, that's what I expected. So I just want to make sure we're clear on this. So I'm going to pick a y value on each side of the intersection, and you're going to tell me. So let's just right here here's my y value for f, here's my y value for g. Which one's bigger, the y value for f on the blue graph or the y value for g? Which one's bigger, the blue graph or the red graph at this point right here? The blue graph, f, the blue graph f is bigger than g. Over here on this side, if I put a y value right here, which one's bigger on this side, the red or the blue? Which one's the bigger one? The red. Okay, so since the red graph is g, on this side, g is bigger than f. And on this side right here, f is bigger than g. The y value at this x value that I put the dots, the blue graph is bigger than the red graph. Does everyone see that? Particularly anybody who said to the right was going to be the answer. Okay, this is important. There's no shame in having a question about this. So then the way I'm going to write my answer, since we have just determined that it's on the left of the intersection where the blue graph has the bigger y values than the red graph, my answer again is the x values that produce that. So it's going to be this interval. I'm shading in orange right here. This interval all the way up to the intersection is where those values are bigger. So I need to write my answer, where is f of x bigger than g of x as an interval? And so the left side of this, the lower bound is negative infinity because they're lines, it never curls back. And then where does it stop? Where does f stop being the bigger graph? Right at 2, right where they intersect. That's the key moment. Now at the infinity part of this, we always put a parenthesis. But what we're going to put at the 2 part of this is related to that inequality. So since there's no equals here, I'm going to put a parenthesis at this side because I'm not interested in where they're equal in that particular problem. All right, well, you're going to have a couple opportunities to figure this out as well. So go to the next one. This time I asked you, where is g of x bigger than f of x? So I'm going to give you 40 seconds to write down what interval you think that's true for. Once again, here's my intersection point. You told me already the intersection point occurred at the x value -3. So is it to the left of the intersection point or is it to the right of the intersection point where the g values, the red values, are bigger than the blue values? This time it's going to the right. You can see if I pick an x value over here, this is my random x value I'm picking, that this y value that goes with g is bigger than this y value that goes with f. So you're exactly right. It occurs to the right of the intersection. So again, I'm just going to shade on the number line. This is my interval right here. And since these are lines and they never change direction, it's never going to stop being that way. And so I'm going to describe the interval now. What's the lowest end of this interval? Where does it start, G being bigger than F? -3, that intersection point. And then it never stops, so we've got infinity. Once again, there's no equal here, so I'm going to put a parenthesis on this side. Anybody got a question, comment, or concern before we hit the very last problem on this section? All right, just for consistency's sake, on this last problem, go ahead and let the blue graph be F again, and let the red graph be G. And answer both questions. Where are they equal? And when is f of x less than or equal to g of x? Okay, so where f of x equals g of x, where those y values are the same is where they cross right here. So what is my solution set? What value do I put in there? Okay, you're going to put 0. You always put the x value that produces that y value. So if you said 2, and that's common, okay, so don't beat yourself up, you're learning, but the answer is not 2. The answer is 0, because that is the value that produces the y value of 2 in both of those functions. So then I want to know, where is f of x, the blue graph, less than g of x, the red graph. So which side does that happen? Is that the left side of the intersection or the right side of the intersection? The right side, you are right. Good job. And so over here, the orange, what I've just highlighted orange, that's where the blue graph is less than the red graph. So that starts at 0. It goes to infinity. What am I going to put at the 0 end of this interval this time? I'm going to put a bracket because I've got an equals right there. So that's what determines the shape of that. Before I click off and say we are finished, is there a question or a comment or anything I need to clear up because I did not do a good job?